Okay, this is chapter 15 notes. We're going to talk about sound. So sound waves, as we discussed before, are just pressure variations in the air. So you have like a cascade of air molecules bumping into one another, and obviously that are the same frequency at which the object is vibrating at, because that's what creates those pressure waves. Then they hit the ear, obviously, and the eardrum then vibrates at that same frequency and sends that signal to the brain, which interprets it as a certain pitch. Here is a table in our book then that gives you the speed of those waves. So for sound, in air at 0 degrees Celsius, it travels at 331 meters per second. At 20 degrees Celsius, it travels at 343. So basically air is more elastic at higher temperatures because the air is moving faster and bumps into itself more, I guess, quicker. So as you increase temperature, you do increase the speed of sound within one specific medium. And then obviously as you change, so helium, the speed is quicker, water, the speed is quicker. As you get into objects that have more elasticity within the molecules, the speed of sound increases. So iron and steel has really, really high speed, which therefore the sound will travel for really long distances. Okay, and when it comes to perceiving sound then, the pitch is equal to the frequency. So the higher the frequency, the higher the pitch. Loudness then is measured in decibels, and it's a logarithmic scale. And the reason it's a logarithmic scale, and we use decibels for that, is because the human ear has such a huge range of hearing. It can hear from like basically 0 to 20,000 hertz of different frequencies, but it can hear a huge range of volumes of decibels. And so what they do is basically you take all that data that's really spread out, and if you make it a logarithmic scale, so if you go then 10, 100, 1,000, you then shrink that data down basically, and you give it in decibels. That's what a logarithm basically does. So, and you can watch a video if you want to hear more about that. I found a nice YouTube video from Khan Academy that a guy explains it very well. But we're just going to use decibels, so 10 decibels would be something you can barely hear, and then if you pretty much double that, you're going to double the sound intensity, which sound intensity is actually measured in watts per square meter. So it's like how much power is there per surface area. But like I said, we're going to use decibels instead because the human range of hearing in watts per square meter is too big. So here is some things that you're familiar with. Heavy traffic would be about 70 decibels. A siren is about 100. A jet engine would be about 140. Next is the Doppler effect. The Doppler effect is going to be really important because frequencies of sound, and we're going to learn later light, can be changed if an object's moving. And you've heard this probably if you've heard an ambulance go by. You've heard a high pitch as it comes near you, and then as it moves away from you, it's a lower pitch. Now we have a mathematical relationship for the Doppler effect, which is right here. And we're going to use that to find different variables in a problem. So this V stands for the speed of sound, which in 20 degree Celsius air is 343 meters per second. This stands for the velocity of the detector, so that would be mostly you if you're listening for a sound. This is the velocity of the source, which depending on what's making the sound would be like a car or whatever it is that's making the sound. And this is the frequency of the detector, so this is basically what you hear in hertz in terms of the frequency or the pitch. So we can do an example problem really quickly. Let's say a trumpet player plays middle C, middle C is 524 hertz. And let's say we're traveling a convertible at 24.6, then what we would do is plug in the frequency of the source is 524 hertz times the velocity of sound is 343 meters per second minus the velocity of the detector, which is you. It doesn't say you're moving, so that'd be 0. Divided by V is 343 minus the velocity of the source, which they said was 24.6 meters per second in the convertible. So if we do this math, we get about 564.5 hertz. So if something's moving towards you, you would hear a higher frequency and therefore a higher pitch, which is exactly what we would expect. All right, I had to put a creepy picture of a bat as well because I think it's fascinating how some animals hear with echolocation. So they hear with sonar. They're able to put out frequencies of sound, and then from the reflection of that sound and the time it takes for the sound to get back to them, they can determine where objects are. And what's fascinating is they can use the Doppler effect. Their ears are finely tuned so much that they can even hear if something's moving away from them or towards them based on the frequency shift of that sound. So they can even use the Doppler effect, which is pretty impressive. The next section of the book is on the physics of music. Those of you that are in band or play an instrument, this might be interesting to you. I'm not going to test you over any of this. It's not in our curriculum, but there's a bunch of information about how this applies to musical instruments that you might be interested in. So if you want to read, it starts on page 411. That might be something to do.